webinar 2, which is a follow-up for an earlier webinar that we had on the 21st of April 2014. My name is Shadi Atia, and I work as Professor of Architecture and Sustainable Building Construction in Belgium, in Liège. And today's presentation was started as a beginning of an initiative or a project called Dynamic RENOWAVE between Liège University and Université Catholique de Louvain in Belgium. And this project, the Dynamic RENOWAVE, was entitled Life Cycle Assessment and Energy Simulation of Building Renovation Strategies. Earlier, Professor Stefan Petersen and myself, we prepared a webinar trying to shape and carve this framework, and we shared with you our ideas, and some of you interacted with us, and we had this webinar already on YouTube. Today, we have a follow-up for the earlier webinar of April, where Aurora Bertini and Maxime Dasse, two of our PhD students at the University of UCL Louvain and Liège, they will try to delve into a more detailed application or ways of how we can apply this framework so that it can be useful. I need just to give you some context here. We are talking here about a framework that works about, that tries to model the emissions for operational emissions for building and also for embodied emissions. The project is part of a larger initiative, but I can invite you later to check the website of the project. Another important announcement that I would like to tell you that between April and today, in end of May, I got so much contacts with different initiatives and contact organizations, and one of them was the GLOBE initiative. And this GLOBE consensus initiative, they decided that they would like to join our project, and here they are looking to have a global consensus on sustainability in the built environment. We are talking here about 150 nations, more than 5,000 experts, and we will all work together on ways to quantify greenhouse gas emissions in the building stock, whether on the level of embodied carbon, the section A, or section B, or section C. Now, allow me to give you some idea about where we are going, where we are coming from. Like I mentioned earlier, we had already our webinar in May, where Professor Petersen and myself were presenting the framework in one of its earlier drafts. Today, we will have the presentation of Mrs. Bertini and Mr. Dasse. And both of them, after they will present, we will have a Q&A session so that we can get your feedback and interact with you on your comments, advices. And then we will have the last stage, which will be the report. We will write a report in the form of an open access report. We already invited many experts who were so interested after our webinar number 1, who joined this report. And I'm very glad that they're attending today. So don't hesitate to continue providing your feedback, your advice, so that we can formulate this report and publish it by the end of June as a collective open access report. Anybody can use it, and from there can pick it and build on it to develop maybe a more specific, more customized, or even a more universal framework that allows for a calculation for greenhouse gas emission in a consistent way and based on international standards. So allow me to introduce today the first speaker of the today's webinar. It is Mr. Maxime Dasse. He's an architectural engineer, first-year PhD student. He's enrolled in both universities, Liège and UCL Louvain, as PhD student. His main supervisor in UCL Louvain is Professor Émile Goubeau, and he's working in the lab Architecture et Climat. And the second supervisor is myself, Shadi Atia, working at Liège University in the Sustainable Building Design Lab. Maxime has an expertise in building life cycle assessment and parametric design. He is a very savvy programmer when it comes to Python. And he is also a member of the International Energy Agency Annex 89 on ways to implement and calculate the total life cycle carbon emissions in buildings. So if you want to meet him, he will be in Berlin in June. So he's one of our key team members. The second presenter of today is Aurora Bertini, Mrs. Bertini. She's also an engineer, but a building engineer in the first year. She's enrolled in both universities and both labs, like we mentioned earlier. And she is specialized in building energy modeling and building physics. Her master's thesis was about shading systems and control algorithm for shading systems. And she has an expertise in general in building physics and building systems. She will be the, let's say, expert who will work on the operational emissions in this project. And she is more familiar with the modeling techniques and knowledge related to greenhouse gas emission calculation for the operational phase or the use phase of building. Well, without further ado, I will invite the first presenter to start to share his slide and start to elaborate on the framework that we discussed earlier.
All right, thank you very much, Shadi, for the presentation. Can you hear me? Can you see my screen?
No, I think, yeah, the case study. Can you move one slide forward? Super, the floor is yours.
Okay, perfect. Well, good afternoon, evening, morning, from wherever you are, everyone. It's a pleasure to be here and present the result of our work so far. It's still a work in progress, as Shadi mentioned, so we will be very glad to have your feedbacks on it and advices on how to improve all of this. So first, I'm going to give you a tour of the structure of the presentation, just so you're not lost along the way. The framework itself is divided into several steps, which will be the same structure for this presentation, interrupted here by punctual additional information, such as information on life cycle assessment or meteo weather modeling. A case study will be used to illustrate the application of this framework along the way. It is based on the best test 600 developed by the ASHRAE 140. We simulate a renovation of this case from a poor energy performance to a passive energy performance. All of that in the Brussels climate, as we are more familiar with this. All right, so first, the first step, which is the approach of modeling that you are going to use. Two approaches can be used. First, the bottom-up approach based on the climate change scenarios, and second, a top-down approach based on greenhouse gas emissions budget. So taking the whole planetary boundaries and dividing them to derive a budget for the assessment of the buildings. First, for the bottom-up approach, the aim is to have a baseline scenario, then improve the design to try and have better versions as we go up. Well, it's then also important to identify some benchmarks for later comparison. This step must be done in the early stages of the assessment of buildings to have a comparison point that is as accurate as we want based on the scope of the study. The different climate change scenarios that we recommend are based on the IPCC RCP 4.5 and 8.5, which were published in the annual report of the IPCC from 2021, the 5th and 6th. And the time scale for taking the scenarios are more like 2030, 2050, and 2100. For the benchmarks, we recommend national or continental sources. We have the EPISCOPE database for Europe, for example, and Tabula as well. But this is something that is really regional. So we recommend that in your own country, you identify sources of benchmarks that are applicable for the model you are modeling right now and assessing. It is important. I forgot to mention it, but it's really critical actually to do both those approaches. So the bottom-up and the top-down approaches to have kind of the uncertainty ranges of the results that you are going to have to produce based on this framework. So for the bottom-up, it's done. For the top-down approach, we recommend the global warming potential metric, as was recommended by the IPCC, which uses generally kilograms of CO2 equivalents as a metric. So of course, you are all, I guess, familiar with the Paris Agreement that aims to limit the temperature rise to 1.5 degrees by 2050 and 2 degrees by 2100. This gives us a boundary in terms of CO2 equivalence emissions of 500 gigatons per year, that is. This is like the boundary that we were going to divide to identify the GHG emissions budgets for the construction sectors and later for buildings. This is a difficult task. So for now, no commonly agreed budget exists. Nothing is sufficiently advanced to provide exact data on what your building, what is the budget for your specific building. However, we have Stefan Peterson collaborating with us and present today, and Greg Foliente, who both work on trying and defining budgets for buildings. So I will invite you to check their work. It is extremely interesting and really reliable in this context. For the case study that we are going to model to present here, we will use only the first approach, just because of a matter of time. Otherwise, it would have taken forever to present. So the second step is identifying the climate, the location. Then, so first you have weather data, in which you have a first choice to make, which is to exclude the urban island heat effect or include it. And based on this choice, you can then, of course, you also need to select your city. In our case, it's going to be Brussels, of course, but here are the different cities that we recommend based on the standards. So for the weather data, we recommend Meteonorm as a source of weather files to model your weather conditions, your climate. And for this case study, we chose the weather file for 2020, so current, let's say, and 2050 that are in agreement with the RCP 8.5, sorry, and also the file for 2100, of course. For the weather data sources, bits of more information, additional information about Meteonorm. So Meteonorm is a global project that aims to provide climate data for lots of points on the planet. Here is the map of all the points that they currently provide. They cover also different periods, so historic, in the past, contemporary, and future, up to 2100. And they currently implemented the scenarios of the IPCC, RCP 2.6, 4.5, and 8.5. You can also, if you can't find your own weather data in that, we advise you to model your own weather file using the approach derived from a paper from Dutroux et al., which consists in taking a global model and then dividing it to reach the scope that you want. It may be not only local, but regional to a continent, something like that. So we invite you to check the reference. Step 3 is characterizing the actual building that you are modeling. So it starts with, of course, the functions that you want to model with its occupancy schedule. Here are the different occupancy that we propose, that we recommend. And for the schedules of those occupancies, you can check the ASHRAE 189 and the ISO 17772, which are a reliable source of schedules to model for the energy performance this time. Then you have the geometry to define. You can choose between taking a real building as a case study, which is the more complex option, of course, or choose a more simplistic approach and process room per room with a shoebox more approach. It is either residential, which will be multi-zonal, or single zone. And here, for our case study, we take this approach, of course, with the best test 600, which we recommend as being the case study, a benchmark for case studies. The first step is defining the structure and the finishes, so kind of the material step. We will leave the envelope of the building for a bit later. So for the structure and finishes, we propose to you to choose them from between 3 possible options. So either a light structure, a medium structure, or a heavy structure. And for the finishes, pay attention to consider the finishes of all the pertinent building elements. In our case, we are going to take a landscaped office and model a shoebox based on the best test 600 with a light structure, wood frame in this case. A bit more detail about the different sub-steps. So first, the geometry. Here is the dimensions of the best test 600 that we remodeled for this occasion. We recommend that you base your models on archetypes that are as local as possible. So you should identify, we don't have it for everywhere, but we are developing in the SBD lab an archetype database for Belgium. So probably that some researchers are doing the same thing for your own countries or regions. So you should base your models on archetypes that are as close as possible as to what you want, with their dimensions as function of the surface that you are needed to model based on the program and the number of people that you are modeling. Pay attention to choose between single zone or multi-zone. Multi-zone can be highly complex, but then it is more detailed and much more realistic in some sorts, whereas the single zone can be much more as a simplistic approach. Then, of course, pay attention to adjacencies and the orientations. If you model a single zone, then you will have to model very carefully the adjacencies of this zone. So if it is if it bounds the outside of the building or just another room that is then adiabatic, probably. For the orientations, we suggest that you take the worst case. So you have the worst case scenario, and that is sort of the low boundaries for your research. It can only improve after that. For the third sub-steps for the materials, so we take the light structure, a timber frame structure. We are aware that simplifying the structure into only 3 levels can be a bit too simplistic, but each structure must of course represent the model must represent, a constructive system that is accurate when you model to have some sort of precision to be accurate in your results. In this case, for the case study, we took a timber frame that with the quantities that are modeled here, and we renovated it to improve the performance. So we almost doubled the glass wall to the insulation thickness. We went from single glazing windows to double glazing windows, and we added PV panels to the top of the case study to produce its own energy and reduce the operational burden. So for our building envelope, we go from the poor energy performance to passive house standards that we base on the passive house standard, a Dutch one. And for the performance level selection, which is the heart of the 4th steps, you should choose your performance level, your desired performance level, based on the climates that you are modeling, that you are located in. So for extreme climates, of course, it's going to be more difficult to model to achieve like low performance because the comfort and the limits to the life are higher. Typically for Alaska, for zone 7 and 8, actually, you can't reach a sea level because you need to be extremely performant. Here for the materials, you have for the parameters, actually, you have here the initial parameters. I'm not going to detail all of them. With the actual new performance that we achieve, you see that mainly we have a very increased U value, which goes from 0.5 to 0.15. Once those steps are completed, so once you are at the end of the step 4, it is the time
to... Decreased U value, you wanted to say.
Decreased. I said increased? My bad, sorry. Thank you for pointing out. So once you're at the end of the step 4, it is the time to start thinking about the coupling of embodied emissions and operational emissions. So we recommend for a full life cycle assessment that you take the stages A to C. We exclude here the D stage because of the uncertainty linked to it. We assume that it is not mature enough right now to produce reliable data for the calculation. We prefer to restrain the scope to the A to C stages. The embodied stages are going to be the one in green, so A1 to 5, so the full A stage, and the B4 and 5. We do not include the use, maintenance, and repair in this thing because the data is too uncertain in some sort. We also include the whole C stage. For the operational energy, the B6 is sufficient. But of course, if you have additional data, you should do the most that you can. So if you follow these steps, it's already very good. But if you can go further, it's always encouraged to try and go further. Here for the embodied stage, so once we have defined the materials, we can start calculating it. So for the case study, we take only the stage A1 and 3 and the stage B3, but also the end of life with the C3 and C4. To perform it, we recommend that you use EcoInvent and preferentially with Brightway and Activity Browser. If you don't know, EcoInvent, this is a very well reputed, very popular database based on a process approach that is going to model that is helpful to model the life cycle of various elements, not only building. It is not a building oriented one, it is generalistic, but the result is still accurate enough for to model for buildings. Brightway is a package of Python from Python that can be used to bridge Python and EcoInvent. It is extremely powerful. It is as it acts as a database manager that can actually create new databases based on the process of EcoInvent, which is useful to model your actual case studies and link it to everything and do it in a parameterized way, which is much more efficient. Activity Browser is kind of an interface placed on top of Brightway, which allows you to have a visual interface instead of a script one. It is very powerful, but quite recent and not completely done, like not completely finished right now. So there is still some bugs, but for the basic calculation, it is extremely powerful. For the allocation, for the linking method of the different process of EcoInvent, we recommend here that you follow the norms, actually the standards. So EcoInvent proposes a linking model, system models, which is based on the EN 15804, which is quite close to the allocation cutoff from the other allocation model that they propose, but that is more closer to the standard. For the calculation method, you have a lot of them available for you, but we recommend that you follow the IPCC in this one. The IPCC produced a calculation method in 2021, which is implemented in EcoInvent, for example, but also in most other databases. So we recommend this calculation method. There are some issues. Okay, I'm sorry, if you could get your microphone right now. Thank you.
I will take care of the microphone.
Perfect, thank you, Shadi. Pay attention that here the transport is often really difficult to model, to get your materials that you use from the place that they are, where they are produced to the construction site, if you have a real case study. But they do have hold a share that is quite important. So do your best to try and include the transport, but we know that it is quite difficult, and we'll try to come with a method to do it more accurately and more easily. Then some issue regarding this calculation. So first is the EPDs issue. So EPDs are a new, not that new, but a common way to derive data to get data from materials to model to perform an LCA. However, those EPDs were proved to be not that reliable as they were produced directly by the industries. Usually, you don't have all the information you need in there, and very frequently, actually, the numbers and the data that you are going to find in those can vary a lot from one EPD to another. So what we recommend is that if you can't find the actual data in robust databases such as EcoInvent, then you should try and get it from EPDs, but not from only one EPDs, but try and get several, like a dozen or more EPDs to model your data, to try and get the most robust data possible. But be aware that it won't be perfect. It will never be perfect. Then there is the HVAC modeling issue. We know that right now HVAC systems are not very well represented in generic databases, and it's hard to find data for that. Currently, we can recommend and redirect you to One-Click LCA, which proposes some modeling solutions for HVAC systems, but also to the work of Sébastien Laureau, which is a PhD student at the end of his PhD, and he's working especially on that to find the best data possible and produce a database for that. Then you have the bionogenic carbon issue, which is quite recent and start to be implemented in standards such as ISO. There is lots of debates regarding the approach to use, but we recommend to take a -1+1 approach. So for materials that will capture CO2 during their life, their primary life, such as timber, we recommend that you subtract the CO2 captured from the calculations. But then at the end of its life, when it's disposed, when it's being recycled or anything, when it's being disposed, sorry, you should add it at this point. So in the end, it balances itself, but the whole advantages is to store the carbon durably, sustainably into buildings. So let's model it that way. And finally, for the final issue is the data type. This is something that is still a big issue for the results of life cycle assessment. You may not notice, but databases of LCA are usually based on one of these approaches. Either process, which is the case of EcoInvent, or input-output, which is a top-down approach. It is proven that actually those two approaches can produce very different results. And so it is recommended to try and find hybrid data. But currently, the only hybrid database that exists for buildings is the EPIC database that was produced for the Australian building stock. Therefore, it is reliable to some extent. Some projects of the work of Fabien Prideaux is currently trying to extend it to Europe, but it is still a work in process. For now, then, EcoInvent still is the best choice, waiting for an extension of those databases. After all these calculations, and with the case study that we took, we arrived to those results for the global warming potential with 3 possible scenarios. So you see that just for the renovation of only one small case study, only one room of 48 square meters, we can reach already a ton, like 1.2 ton of CO2 equivalents that are released into the atmosphere just to produce the insulation and the glazing and the PV panels. Now I will leave the floor to Aurora Bertini, who is going to present the HVAC system, the operational part.
Thank you, Maxime. Until Aurora checks in, I just give you some information. We had on the peak of today's participation, we had reached 72%. We are now around 66. Right. And just to increase the interaction, I would like to invite all participants, if you have any questions, to directly type them in the chat, because I'm receiving a lot of likes and hearts and a lot of different emojis, but they're not appearing on for everybody. So don't hesitate when you like something, if you have a question, if you are inspired or have an advice, to directly type it so that we can have a rich Q&A after. I guess Aurora is ready and we can continue.
Just confirm me if you can see the slide. It's okay? It's
excellent.
Okay. Okay. Okay, so Maxime talked about the first 4 steps of the framework. And now I will move on to with the step 5 that is related to the HVAC systems. Like in the case of the envelope, we can have 3 different levels of performance, the poor, the low energy, and the passive house, that correspond to different energy labeling levels. In the case of the poor, we considered that we take the existing condition of the building without mechanical ventilation. And the first step to improve it is to move to the low energy level that allows to introduce more performing gas boiler, like the condensing boiler, to introduce air conditioning and mechanical ventilation. This performance can be improved even more, introducing the heat pump, the on-site renewables like photovoltaic and solar collector, to include in the model the district heating and the cooling, and the possibility to have a geothermal network. In this case, we start with a condition with a gas boiler with a COP of 0.85. There is natural ventilation, but not mechanical ventilation, and there are no renewables. So we suggest a renovation with air-to-water heat pump with a COP of 4.5. The natural ventilation is considered too, but with some constraints in terms of temperature. So we say that natural ventilation can be used in the intermediate season, like spring and autumn, so that it has a lower impact on the heating energy use. And in the heating season, the natural ventilation is substituted with the mechanical ventilation. And finally, we introduce PV panels with a surface of 4 square meters. So now we have all the inputs to run the simulations. The energy, we have all the inputs for the building energy model also. And so we can move to the calculation of the operational greenhouse gas emissions. In this case, we decided to focus mainly on the step B6, that is the operational energy use. And to make this calculation, what we need is to have the heating, cooling, mechanical ventilation, lighting, and appliances energy uses. In this case, since we made the hypothesis of not having a cooling system, we will only take heating, mechanical ventilation, and lighting and appliances. There are other parameters that can be included in the model and that we did not model in our case study because they are, let's say, recent in terms of technology development. These are, for example, the case of the storage. We can have, for example, as technologies, water tanks, phase change materials, and batteries and fuel cells that can be used all as thermal or energy storage. In the case of the water tanks, nowadays they are coupled with solar energy and heat pumps to produce hot water. And if we want to include them in the model of our building, what is important to consider as parameters is the volume and the hot water temperature that are related to the quantity of energy that we can store, and the tank insulation that is related to the losses of our tank, and also the time period for which we will have the storage of the energy storage. Another technology that we can consider and include in the building is the phase change materials. Phase change materials can be used and are used to minimize the variation in electricity energy use between day and night. And there are two different groups that we can have, the passive and the active. In the case of the passive, we don't have any other, let's say, energy consumption, additional energy consumption, because some examples are the fact that these phase change materials are mixed within the composition of gypsum wallboard or within the concrete to increase their thermal storage capacity. Or phase change materials can be active and they can be included, for example, in the stratigraphy of the PV panels or in floor heating systems. And finally, another solution that we have is batteries and fuel cells. Batteries are usually used for short-term energy storage, while hydrogen is used for long-term energy storage. And nowadays, they can be coupled with PV panels. And for example, it is possible to produce hydrogen during summer when we have a lot of, we should have a lot of sun. And it is possible to store this hydrogen and use it during winter when we don't have a lot of sun, and so the battery storage is poor. Other parameters that can be included and considered are the ones related to the energy mix. What we can observe is that the energy mix can vary during time, and this variation depends also on the policies that the governments can adopt. And the more we aim to reduce the greenhouse gas emissions, and the more the policies are in that sense, the higher is the contribution of the renewables in our energy mixes. And it is important to consider the evolution of the energy mix in the calculation, because this variation had an impact on the calculation of the greenhouse gas emissions, the operation and the embodied. And finally, the other parameters that can be considered is the carbon tax and the carbon threshold, because we are moving towards a context where we are fixing some carbon caps, emission caps. And this is the case, for example, of Europe, where it has been introduced a trading system for the emissions. It is a sort of market mechanism where CO2 has a price, and Europe fixes a cap of emissions, and companies have to buy allowance for every ton of CO2 they emit per year. This allowance can be exchanged between the companies, and the aim is to reduce the greenhouse gas emission in Europe. Before this approach, this carbon market was mainly adopted and for power generation and energy intensive industries, like the ones producing, I don't know, iron. But from 2027, they will be introduced also for buildings. So that's why it is important to consider this aspect also in our work. And finally, related to carbon threshold, for example, we can mention that the RE 2020 that is fixing a greenhouse gas emission threshold for energy consumption. And this threshold depends on the type of building we are considering. So it is different for single-family houses, apartments, and also is different if we can include district heating within the building systems. So now we can move to the last step of the framework, that is the evaluation of the scenarios. We have identified three main indicators to evaluate the scenarios: the operational energy, the greenhouse gas emissions, and the cost. Today we will mainly focus on operational energy and greenhouse gas emission, and we want to consider the cost. In terms of operational energy, one of the metrics that we can consider is the energy use intensity. And if we analyze the results that we have obtained for this simple case study, what we can see is that effectively the renovation allows to reduce the heating energy use of the building. And it is possible also to generate electricity on site. That is the yellow part of the graph. We can also observe that the energy use intensity for heating is reduced moving towards the end of the century. This is because of the rise of global temperatures. And from this trend, we can insist on the fact on the importance of making simulation using different weather files that consider also the climate change effects, because renovation have to consider have to be robust and consider also we have to consider its effectiveness in the long term. So consider also the 2050 and the end of the century performance. Another metric that we can use to evaluate the operational energy is the primary energy. In this case, we mainly focus on the net primary energy. And we can observe that if in terms of energy use, the difference between the base case and the renovation scenario is very high, in terms of primary energy, it cannot be the case. This is because maybe because of the primary energy factor that we use. In our case, the electricity is penalized compared to natural gas. So our renovation scenario that use the heat pump that is mainly fuel is electricity is penalized in a certain way. So that's why we have a small difference between the base case and the renovation scenario. In terms of greenhouse gas emissions, from the results of the energy use intensity, knowing the emission factors, we can calculate the operational greenhouse gas emissions. And as we were expecting, the emissions are reduced compared to the base case, mainly because we have a reduction in the heating energy use intensity. Of course, these results depend on the emission factors, and in this case, we considered the Belgian energy mix. These results can vary according to the country we are analyzing. Finally, we can consider embodied and operational greenhouse gas emission together. In this graph, we have shown the progression of the cumulative greenhouse gas emissions. And we can observe that in our case, the embodied greenhouse gas emissions are small compared to the operational. And this is because also of all the hypotheses we did in our case study. So we neglected the transport phase, the construction, the replacement and repair and maintenance. And also we neglected the contribution of the HVAC system in terms of embodied greenhouse gas emissions. That's why this contribution is small compared to the rest. Finally, we suggest concluding the study with the sensitivity analysis and uncertainty analysis. This is because, as we saw, the process is very complex. It involves a lot of parameters. So it is important, first of all, to run a sensitivity analysis to identify the critical parameters. And it is also important to quantify the uncertainty that is linked to the complexity of the process and to evaluate the robustness of the results through the uncertainty analysis. So with this, I conclude the presentation. I just want to remind that this is a framework that is, as was said at the beginning, is a work in progress. That we presented in our first webinar, and now we shared an example of application. But yes, it is a work in progress, and we are, of course, open to all your feedbacks and your suggestions to improve it. So thank you very much.
Thank you, Aurora, for the presentation. Thank you, Maxime. I will start sharing the slide from my side. Just make sure that everything is all right. Heads up, can you see yourself? So
yes, we can.
Very good. Thank you very much. The presentation really provided new insights, and you managed to push the earlier initial framework. So it's now time for Q&A. I invite all participants to get engaged. Don't hesitate to write your comments in the chat. We will read the chat in order. But maybe I think Professor Stefan Pettersson had 2 comments already. We can start with him to initiate the Q&A. So Stefan,
sure. Thank you very much, Shadi. And thanks to the presenters. That was excellent and really, really interesting. I had a lot of notes on different things. No, I was just putting in a few comments along the way regarding the weather data. And you recommended a meteor norm, and I also been using that a lot. I think there are various sources that you can get this data from, and I just put a few more into the chat where it's free, and you can just go and download these things, and that's at least what we do. So there's always a discussion about which scenario should we use. Is it 4.5 or 8.5 or whatever? Maybe, I don't know. What are you thinking about that, presenters, regarding climate change scenarios and developing risk scenarios based on that? What is your take on that? Could you elaborate a little bit?
Maxime or Aurora would like to take this call. If not, you can shuffle it to me.
No, I'm just not sure if I understood the question. So
the question was, you know, in the IPCC scenarios, there's RCP 4.5, 8.5, and so on. These socio-economical models of different projections of what might happen in the future. So the question was, what is your take on choosing one of those, if this is correct, Stefan?
Yeah, exactly.
Yeah, actually, what we in this example, we decided to choose for the worst one, that was the 8.5, because considering the current global situation, we are, let's say, is the most likely to happen. Let's say, so we decided to go for that, and yeah, it's the most let's say, somehow we are conservative because it's the worst scenario we can have compared to the.
Yeah, you're absolutely, and I agree with that. I think that's a very good rationale, and I was expecting to hear that. Less than a year ago, there was another report coming out that the Gulf Stream that goes above the British Islands and up towards Norway and that way around, that there's a high risk that this could stop in our lifetime, this Gulf Stream, which will mean that the temperature in Northern Europe will drop at least 5 degrees Celsius. So that's the opposite scenario, you could say, of 8.4. So, you know, there are extreme scenarios in both directions. Have you heard about that?
Honestly, not.
No?
No.
But that's a new scenario that has come in, that if the Gulf Stream stops, we actually have an opposite scenario. And you know, that messes up our whole assumption about resilience, basically. So this is very complex. And what is the common denominator in terms of building renovation when we look into a future that could be super cold or super warm? Yeah, I don't want to take more time on that. It was just to say this is a super complex issue, and we should think a lot about these scenarios, I think. The other one was just a link to, now there was a mentioning, I think it was you, Maxime, who had something on embodied carbon of HVAC, which is difficult, or there's not much data, at least, available to have an idea about how much that is. And I just put a link to a report in the chat. It's in Danish, I'm sorry about that, but at least we have some mandatory calculations that we have to do, and there are some conservative benchmark numbers that you can use if you don't know what your embodied carbon for your HVAC systems are. So I guess if you can run that through an AI and get it into another language, you could get an idea about at least how we try to deal with that in Denmark for now. That was my two initial comments. I have several more, but let's hear from others as well.
Thank you, Stefan. Great. So just to wrap up, there was a comment shared. I will share these links in the report. One was about the Copernicus climate data set, and another one was a report that is also in the chat. We will have it shared in the report with everyone. Now, moving to the following question in the chat, I have a question from Kadim Noman. Thank you for the excellent and informative session. Brightway seems quite interesting tool. Can you provide a brief introduction about about its capabilities, and can it be used in BIM application such as Revit? Maxime.
Yes, I can answer that. And also the question of Philippe Lemarchand, which is related. It's the last question in the chat. So just to mention the question, one of the advantage of EcoInvent plus Brightway plus Activity Browser compared to commercial software, such as One-Click LCA, question mark, I presume they are open source. Both those questions are linked. Yes, Brightway and Activity Browser are both completely open source, and you can contribute if you have the coding skills required. And this is, I mean, the first advantage compared to One-Click LCA, because it's not a black box. You really see where everything is coming from, and you can tweak it if you know where to act. So that would be the first advantage. Of course, it's not completely white, because as it is open source, it is often less quickly developed, let's say, and they have less resources, as the majority of the developers are, I think, volunteers on this one. So that's for the open source nature, and that open source nature is linked to Revit. I personally have never used Revit myself, but I know that several research are made right now, currently, to kind of introduce into LCA and live LCA calculations to BIM tools such as Revit or Archicad. So there may be, I don't know a precise one, but there may be some tools that enables to make a bridge between Revit and Python. And once you have this bridge with Python, if you have enough coding skills, you can probably bridge it with EcoInvent through Brightway. However, I don't know myself ways to do it directly.
Thank you, Maxime. Well, there's another question here about HVAC modeling, and I will take that. I just say that so far what we will do in our project, I will ask Maxime and Aurora to find technical sheets for the systems that they are going to install. For example, if they will introduce a heat pump, if they will introduce a mechanical ventilation system, if they will introduce district heating or cooling, just look for the technical sheets. Also, I recommend the CIPSI TM65. It's a very good standard for building services, which is associated with emissions. And since we are focused on greenhouse gas emissions, we will find data. And then I will reiterate and re-articulate exactly what Maxime was saying earlier, is that we can use the EPDs, but then with the generic nature of the EPDs and not the specific nature of EPDs. So for sure, we still have challenges with the refrigerants. There will be something difficult, but I think it's very easy. Just start with getting the components of the HVAC systems, identify them, then try to get the weight of these components and the major materials that form them, and look at the transportation, look at the embedded emissions. With all what I said, technical sheets, EPDs, you can make it, especially that in our project, we are focused mainly on residential, so we will not have these gigantic HVAC systems that we can find in an office building with a chiller and so on. So moving to the following question, again, Stefan, I have you talking here about the threshold with the square meter, and you mentioned it's not the appropriate metrics. Maybe just word it again. We have it in the last presentation, but just what's your say on that? Maybe Aurora has a comment, because still we need to have a generic framework that allows for different metrics for reporting.
Yeah, I think so. That could be a solution for. But if you want to count it as per square meter, as we I don't know, it skews kind of the picture of everything. I mean, you can have a 1,000 square meter large building that per square meter fulfills 2.5, and you can have a 100 square meter building that also fulfills 2.5. But the 1,000 square meter building is absolutely polluting much more than the 100 square meter building. And that's the main problem with this metric. And it's actually also a problem because it's easier to fulfill a requirement per square meter the more square meters you build. So you get more square meters to divide by. So it actually pushes us to build more square meters to fulfill a weird requirement. And I've made a lot of analysis on this, and I'm trying to push that a lot internally in Denmark. Like, it's very difficult to understand this simple math, and I'm wondering whether it's me or what are your thoughts about this?
Aurora, you have anything to add?
No.
No, from my side, I would say I fully agree. And to be honest, in this presentation, it's obvious that we took the easy path. The easy path is that doing the regular, which was the bottom-up approach, not the top-down. I think I promise that we will work on the top-down approach, and we will include you and others to work it out, because only the results of this framework will make sense and will bring us to drastic and significant, not even significant, remarkable reduction of emissions when we start to think per capita or per person or per occupant. And from there, we can have a serious paradigm shift, and we can go back to the Paris Agreement budget and make more sense of what we are working. Because I think whatever we are doing, if we stay in this first pass, there is no innovation, nothing is new. The innovation will come by shifting, going to the second approach where we have a budget and limitation. Well, I hope this answered the question.
I think so too, Tian. And just to let you know, these days in Denmark, the political system is renegotiating our benchmark. Denmark, which CO2 equivalents per square meter per year for new buildings, 12. For all buildings above 1,000 square meters. And what they are doing now is that they want to set a benchmark for buildings below 1,000 square meters. They are still doing this per square meter, but then they are also trying to differentiate it, like what you said, something about, Aurora, that for different types, it should be different metrics. But that is just screwing the picture even more up. So I don't want to elaborate too much on that. Maybe we could have a separate session on that later. But this per square meter and how much for a kindergarten and how much for a home, it's a super difficult exercise when we insist on keeping it per square meter. So it's yet again another big issue to elaborate on.
I will keep it on the list of potential future webinars that we can work on maybe next year. Thank you, Stefan. There was a question about the earlier presentation. If there's a recording, I replied there is a recording and I provided the link. Following question is for Maxime. Why do you choose allocation cutoff method as EcoInvent library? Which library would you use to estimate embodied carbon of historical buildings still cut off? I don't know if you can understand everything.
I do understand, and that's a very interesting and complex question, actually. First, for the cutoff system that I choose here, it is mainly driven by the compatibility with the EN 15408, 804, my bad. Because this is a framework that is supposed to be global, to have a common agreement on something. So we need to focus and to speak the same language, the language of standards that already exist in that sense. Now, of course, different situations call for different approaches. So for situations such as with historical buildings, that's a difficult one because we don't have that much data about what was. We cannot model it as accurately as we can model it right now. But for historical buildings, I would actually take more of a substitution approach because it better represents markets in the way that they can be saturated and then use different materials for substitutions. But that's it. I don't know how we can model as accurately as we can. I don't know how we can model historical buildings as accurately as we can model them today. Model new constructions and renovations, I mean.
Thank you. And then there's another question for Aurora about the accumulation of the emissions. Just a second. Something about cumulative results sounds bizarre. The linear presentation of cumulative CO2 suggests that you consider operational carbon for base case, for example, in the same of the, suggest to consider operation carbon for base case, for example, is the same for the next 80 years, while probably it is not true, the same for the renovated one. Could you get this question? It is Bazazadeh Hassan.
Yeah, I've seen the question, and the answer is quite simple. The operation is not linear for the next 8 years. It is from 2020 to 2050, and the graph stops at 2050 here. But we modeled it till 2100. So yes, and this is not a linear interpolation, but just linear graph. This was just for the case study to illustrate. Of course, we can go further in the complexity.
Very good.
For example, with considering maintenance or repair, of course, it won't be linear because there are always intervention in the middle.
Yes, the staging of the renovation and how we introduce it on the flow of the history timeline. Very similar question. This study is very complicated with historical buildings when the data about this type of buildings are very, very small. For taking a reducing and efficient approach, I assume, how could we apply this approach in historical buildings? Can we apply this project for historical buildings? This framework, I mean?
It's more difficult. It's still feasible, but using lots of assumptions and simplifications, which will result in much more uncertainty, of course, but at least we will have an approximation. Or if you can get data about, depends on the building, if you have complete data about this from archives or everything, then it's doable fairly easily. But yeah, that's much more rare.
Aurora, it's okay. Okay, there's another question coming back to what was a bit said by Stefan. The question says, thank you for your presentation. On the tools you have presented, you mentioned the LCA methods. What's your perspective on the Paris goal compatibility of these methods? For example, is the use of these methods enough for the building sector to adhere to the 1.5 Celsius carbon budget? What's your take on what should be added or modified to be more Paris Agreement compliant?
Hello, Carlos, first of all, and see you in Berlin, I guess. I cannot answer completely the question, meaning that this approach is as global as we can make it for now, and it will still move and be improved until June. But it would require much more studies, I think, to check if it's in agreement with the boundaries and if we can use it to efficiently model the boundaries. From now on, just hypothetically, right now, from my perspective, I feel like yes, it would be sufficient to check if the building sector can adhere to the Paris Agreement, but I don't know if it can ensure that the building sector adheres to the agreement. I don't know if you see the difference.
Okay, thank you, Maxime, for the answer. Again, another question on LCA from Haitham. He's mentioning that he's considering it a bit awkward to not include A2 impacts when they are mostly already modeled in EcoInvent in the market process. As for A4 transport impacts, at least for Belgium, there's quite a bit of data from the MMG framework. He would suggest to avoid modeling before, as they can account for a big part of the impact, especially in non-residential buildings.
That is a very true remark. Thank you for that. And yes, transport are already modeled in EcoInvent for some processes, not for all of them, unfortunately, from what I saw. And yes, we could have modeled it, but you need to distinguish here the case study that we presented. That was really just a quick illustration of an application of this framework, than the actual recommendation of the framework. The framework does recommend to pay attention to the transport, as it is not that easy to model. In Belgium, it may be easier than elsewhere, but still, it is more complex than just checking for the production stages, for example, for the other production stages. So yeah, we did not include it in the case study, but we recommend that you include it in your case studies, definitely.
Thank you. And another question of Philippe Le Marchand, de Dublin. What would you suggest to estimate CO2 associated to transport? Internally, in their institute of Philippe Marchand, Internally, they are thinking that they should amend their procurement contract to mandate contractors to provide them with their suppliers' locations and modes of transport by kilometer, similarly to local community or commuting transport surveys. Anybody's take here? It's more specific on the transport and how you take it more specifically to make sure that the subcontractors or the suppliers are taken into account and that you make sure that their kilometer associated emissions are taken into equation.
That is, of course, a very precise question, but very interesting. I think, yeah, more collaboration with the industry seems to be the key here, as without having the full, without having information on their supply chain, we can only make assumptions that will be proven to be false or too incorrect to be reliable. So, yes, I don't have any other proposition right now to try and model it more accurately. There is, of course, the possibility of trying to define generic distances, but then again, it's very inaccurate, like very not precise.
Yeah, thank you, Maxime. And I would say my answer here is that I would like at least that when we will work in our Belgian RENOWAVE project, that we will limit the HVAC systems that we'd like to work on. Maybe we take only the heat pump with the district heating and the mechanical ventilation, and we will do our own audits. So we will try to contact 3 companies and try to see what is the transportation mode, so that in the data collection, we try to triangulate. I believe always in the LCA that you must triangulate your data sources, so that from one side, maybe we find information coming from the literature, then we try to get data maybe coming from the producers or the suppliers, which is self-reported, option 2. And then we look at also our own inventory or our own audit data, so that we can have a triangulation of different sources, whether it is EPDs, whether it is the supplier and technical sheets, whether it's literature review or the industry. And we can also look at the database. There's no problem to look at the database like EcoInvent in parallel, so that we try to triangulate or even move it to 4 or 5 sources of information, and to be very specific, so that we can defend these results and increase the confidence in the simulation. And like Aurora mentioned, uncertainty analysis and sensitivity analysis will play a major role in any of these scenarios proposition. I think we are getting to an end. I went through most of the most important questions. One more last final remark for Carlos, when he talked about how can this framework that we are proposing here to make it complying or scientific as possible and in line with the Paris Agreement 1.5. I would say, first of all, we followed some certain strict criteria. We made sure, number one, that we are using international standards, so that the calculation methods and the calculation approach in every of these stages, 9 or 10, 12 stages presented today, they are based on already well-established standards. We are using EN 15804. Maxime also mentioned the 15978, I guess. So this is the number one, referring to existing standards. Second thing, we are following a really open process. We are making these webinars and allowing people to participate, and we already included more than 5 additional authors for our report that will contribute with their comments to enhance our initial framework that we will publish in June. And from there, we can have a team that is open, that is looking to the state of the art, and can look also to the evolution of this framework. So far, I agree with Maxime about the scientific nature of the approach, but I would say an internal critique to our approach that we still didn't follow the approach of the top down, that we have a budget. This is still need to be explored, but we have time. And I think already what we established with the group of experts from Aarhus, from Liège, from UCL Louvain, other universities, they are all welcome. And in the coming weeks, you will find the report published. And from there, you as a user can take it and even improve it and build on it. So we don't have any intention to have an exclusive work here. On the opposite, we will go more into implementation, but we wanted to have an international framework that is well structured, that can allow others to do comparative studies and follow a consistent way. And I think today, Aurora and Maxime, they answered a lot of questions that are causing confusion and not sure, uncertainty, the biogenic part, the type of LCA, and so on, and for sure also the simulation. So I think that's it for today's second webinar on the building simulation or the building energy emission calculation framework that we proposed. So far, I would like to thank everyone for participation. I would like to thank all the participants and the presenters. And we will have this recorded session very soon shared with everyone. And I wish you all the best. And I hope we can start running our simulation and start to have our national targets achieved, and not only from a top-down approach, but also from a bottom-up approach in compliance with the 1.5 degrees Celsius and even the 2 scenario of 2 Celsius degree, which we are most probably heading towards. Best of luck, and thank you everyone for your time, and see you in the next webinar.
Thank you very much, Shadi.
Thank you.
Thank you.
Thank you.